Hello, everyone. Welcome back to Student Talks. And today, the speaker is Sheamol Obeda, who will be talking about real life applications of Fourier transforms. So it's a nice applied maths talk today. And if you have any questions, you can always ask in the chat window, and one of the committee members will raise it, or Sheamol himself will read the chat periodically. And if you're watching this on YouTube, please like, comment, share, subscribe, press the bell icon, all that. And on that note, let's start with the talk. Over to you, Sheamol.
Thank you. Hi. So as said earlier, I'm going to be talking about the real life applications of Fourier transforms. So today's talk will look into how Fourier transforms are used in real life applications, looking at different technologies and different ways of using them. Firstly, to start off with, I'm not a mathematician, I'm an engineer, but engineers use a lot of maths anyway in their day-to-day lives. So this is more an applied talk and talking about how maths and how this specific tool is used in engineering and in data science and in information management and processing. I'm going to start with a brief overview of Fourier transforms and how they work, just for people that haven't really come across it before. But I have a feeling that most of the people watching this probably know more about Fourier transforms than I do anyway. So I'm going to look more into how they're applied and how they're used, rather than the actual nitty-gritty maths itself. So parts of the lecture will go into a bit of linear algebra, into a little bit of data science, but I'm going to try and stick to the applications. Most of the stuff that I'm going to talk about today, I've coded myself or I've used other bits of code from the internet. So if you are interested in messing around with the code and actually seeing how it works, I'd advise you to just take a look there, and I'll provide you with all my code afterwards, just because it is quite interesting and quite cool, but I'm not going to be able to go through all of the details within this talk, just because there's quite a lot of details in how discrete Fourier transforms work and how different user systems and like Python libraries and all that kind of stuff, really. So let's begin. So firstly, what is the Fourier transform? There you can just see an equation, and honestly, an equation isn't really that helpful if you don't fully understand what it means or what it does. You can tell by the equation that you've got some integration, you've got some complex numbers, but it's just an integration function, essentially. So what I want to talk to you about is what the Fourier transform actually does and how it works. I'm going to go through it fairly briefly, but in the notes of this presentation, there's a really good video by 3 Blue 1 Brown, which I'm sure most of you guys have heard of. If you take a look at that, it gives a really, really good, like, in-depth analysis of how Fourier transforms work and what they actually are. But really quickly, what a Fourier transform is what it does is it decomposes a function into its constituent frequencies. So what that means is, normally we talk about signals in the time domain. It can work on any functions, but commonly it's used with a time domain signal. And what it will do is it will decompose this into its frequency domain constituencies. So if you have a signal can be decomposed into a sum of sine waves. And what a Fourier transform does is shows you the magnitude of each sine wave present, or each frequency present. So I've got this really cool GIF here, which quite nicely shows how it works. If you have a function, here we've got a square wave. This square wave is the summation of many different sine waves. Each of the sine waves are at a different frequency, and each of these frequencies are at a different amplitude. So what the Fourier transform will do is it will decompose this square wave into its constituent frequencies, and then the plot itself is showing you the magnitude of each frequency present. So the GIF is just going to replay again. That's just a really nice way of showing you how it will decompose the different sine waves and then what the plot means within the frequency domain. To the right of my screen you can see a few examples of different Fourier transforms. So a single impulse or delta function will just have every single frequency at the same amplitude. If you have a square pulse or a boxcar function in the frequency domain, it will look like a sinc function. But the one example that I want to go through is the sine wave, because that's probably the easiest and the most fundamental one to start off with. So this is just a sine wave. I'm certain that everyone here has come across a sine wave before. So a sine wave is a wave of one singular frequency because it oscillates at that frequency. So if you take a look at the Fourier transform of the sine wave, you will end up with a peak at exactly the frequency of the sine wave, which at this for this example is at about 3. So the magnitude here is 1, because if you go back and take a look at the sine wave, the amplitude here is 1. So you can kind of see how big the sine wave is and how big the component of the sine wave is in the frequency domain. So another example is the summation of 2 sine waves. So this wave looks very messy and a bit horrible to work with. You don't fully know what it is. It's just a periodic function, but you don't know which sine waves it has, the amplitude of which sine waves. It's kind of just a messy little function, which we don't really like to use. However, if we take the frequency domain of this plot, we can see which frequencies are actually present within this function, and we can see exactly the magnitude or the relative magnitude of the frequencies present. We can see that there's a frequency at about 10 hertz, which has twice the magnitude of the other frequency, which is at about 3 hertz. Essentially, what we're doing is we have a function in the time domain, and we're breaking it down and analyzing it within the frequency domain. So that's just a very quick overview of what Fourier transforms are. How they work is slightly more different. How they work, we can go into a lot more detail, but I probably won't go into it just because it's fairly complicated and I won't be able to cover it within a talk. But it works in a really, really cool, interesting way. So if you haven't covered that before in lectures, or if it's something that interests you, I would definitely recommend 3 Blue 1 Brown's video, or just generally looking it up, because the way that they work is really interesting as well. But to begin with, all a Fourier transform does is it takes a time domain signal, or in general, it just takes a function and it decomposes it into its dominant frequencies and shows you a plot of which frequencies are present and at what magnitude these frequencies are present. A really basic use of a Fourier transform is with a sound wave. So talking, music, all of these sound waves are essentially just signals that we hear. The way the sound waves works is a difference in pressure in the air, which causes different vibrations. And we can pick up these vibrations as different amplitudes. And when we talk, all we're doing is we're just making vibrations. So what we can do in the exact same way as how we decomposed a sine wave, we can decompose a sound wave into its constituent parts as well. So this is the transform of a sound wave. If you take a look, most of the frequencies are between 0 and 1 kilohertz. And that's just because that's how the human voice works. That's the kind of frequencies that we talk at. And most human hearing is between 20 hertz and 20 kilohertz. So that means we can hear different musical instruments, we can hear different harmonics, we can hear what we can hear, pretty much. So all this is showing is this wave is just someone talking, and this is the decomposed signal of someone talking. However, as you can see, after the 1 kilohertz point, large frequencies at small magnitudes are all present, and all of this is just background noise. All of these frequencies, all these large frequencies are here, and they're just due to the recording, they're due to background noise, and they're due to the way that the microphone picks up different sounds, but they're not actually needed, and most of the time they're not actually wanted. So this is coming to one of the first applications of Fourier transforms, which is, I say, it's a fairly real life situation example, mainly because I've used it before and it's quite fun to mess around with. What I've done is I have a spectrum analysis app on my phone. All that does is it just takes the Fourier transform of a signal of whatever it's hearing, and it will tell you which frequencies are present and at what magnitude, as a Fourier transform would do. But the reason that I did this is because of the fact that I was at a gig, or I was setting up a gig, and I wanted to know why we had so much noise and so much feedback. And what you can do is, if you have your Fourier transform of your signal, of whatever you're listening to, you can kind of hear that there is feedback and noise in the signal, and you want to try and figure out exactly where this noise is coming from and which gain you need to reduce. And what I mean by gain, that's a musical term for essentially amplitude. And you kind of want to find out which gain you want to reduce the feedback in the system. What feedback is, it's when you have a signal which is going back into the system because it's being amplified too much, and it keeps on going through multiple times and gets louder and louder, and it makes a really horrible sound. I'm not going to play an example because it sounds fairly horrible, but it's one of the things that as a musician you really don't want. So what you can do is you can use a simple spectrum analysis app, and it will just show you exactly which frequencies are being amplified, and all you can do is just turn down the gain and you'll have some nice crisp music. It's also the exact same way something like an equalizer on your phone will work, and all an equalizer does is it just increases the gain at different points, different frequencies, so that you can have music that's more bassy, or you can hear more of the high tones and just have a nicer sounding sound. So that's probably one of the most simple ways Fourier transforms can be used in day-to-day life. But now I'm going to move on to a more engineering-y example of how we'd use a Fourier transform and where it's physically used in situations in like modeling. So as you can see on my screen here, we've got a sine wave of varying frequency. So it starts off a very low frequency, and then it will go and slowly become a high frequency signal. This signal, it's a fairly common signal that we engineers like to mess around with and play around with, because you can do fairly few powerful things with it. So if we have a model of a system, for example, a physical, tangible model of a building, and we have a signal generator, if we send out this signal through the signal generator and into the building, we can see what frequencies the building resonates at. We can see exactly what happens to the building at different frequencies. The reason why we use a varying frequency sine wave is due to the fact that we don't just want a single back and forth oscillation. We want to be able to see a range of different values to see what will happen to the model. And an example of this model could be a structure or a bridge. And we, in our labs, we use tiny 3-story buildings, and we'll just send a signal like this through the building. And then we'll use a spectrum analyzer to analyze the signal coming back from the building itself, from the model itself. The reason we do this is we want to find which frequencies the structure or the building resonates at, and then we can add dampeners to the building itself so that it doesn't resonate at that frequency. So we can shift the frequencies up or shift the frequencies down, depending on what frequency we want it to resonate at. So this is looking into something like an earthquake. If you have an earthquake is normally at a very specific frequency, and you don't want your buildings to topple due to these earthquakes that are happening. You could always do this analytically using differential equations, but I mean, we're engineers. We like using models and we like messing around with different systems and electronics and equipment and stuff. So we do it the physical way because it's a lot more fun and you get a lot more physical intuition from it. But going back onto the point of resonance, this is a very classical engineering example of resonance, trying to find the resonant frequency of a structure. So this is the Tacoma Bridge. And in the 1940s, I think it was, this bridge was made and it started oscillating back and forth really badly with really, really big amplitudes. Eventually, this bridge collapsed. Nothing too bad happened. I think one car was damaged and someone's dog died, which was pretty bad, but not the worst it could have been. But this was caused due to just a 35-mile-an-hour wind. And this is due to the resonance and due to the vibrations of the bridge. Using spectrum analysis and using something in the time domain and using a Fourier transform to analyze it, we can see exactly where the resonant frequencies will be. And that's why Fourier transforms can be so powerful, even in physical situations like this, because we can see exactly which frequencies buildings and structures will resonate at. Okay, so going back to sound and going back to the sound waves and back to my first example of human speech. So this image here is a spectrogram. And what a spectrogram is rather than having just your time domain and your frequency domain plots as two separate plots, this combines them into one. So what we have along the bottom, along the x-axis, is your time frame, and along the top is your frequencies. This is the different frequencies present in this audio sample. And then we have the color code at the side. These color codes show the magnitude of the frequencies present at that specific point in time. So as you can see, the higher frequencies up here are not present in the speech. And if I go back a few slides, as I highlighted here, this is everything that's being highlighted within the spectrogram. Whereas these lower frequency points here are going to be very brightly colored, which is this part here, why this part is all brightly colored. But the main issue with the frequency domain plot, sorry, like this, is that this is all of the constituent frequencies put together, but it doesn't help you figure out what the person is saying. It doesn't fully help you analyze what's going on because it's the entire sample all shoved down into one plot. So you've gone from time domain to frequency domain, which is very helpful, but then you've lost the essence of what was said and at what order it was said, unless you do an inverse Fourier transform and go back to the original signal. So this is where the spectrogram comes into play, because we still got the time domain along the bottom, but then we've got the frequency domain along the top, along the y-axis, which means that we can see exactly which frequency was present at which point in time. And the reason that this is really useful is if we look at the way that humans talk and we want to use something like a speech recognition software, we don't just want the frequencies present, but we want to know what was said and when it was said. So what we've done is we've taken a sound wave and turned it into a 2D matrix. And then we're using this matrix to figure out what was said at which point in time, which is really, really helpful when it comes to speech recognition softwares. This is kind of like the basics of speech recognition software. There's a lot more nuances and there's a lot more detail we can go into. For example, all of the noise in the system we don't really want. The noise isn't really useful. It's kind of just a signal which isn't necessary. So we need to make filters and cut off for that. And this form of speech analysis doesn't really work with different accents and different ways of speaking. It's kind of just, this is how someone talks. And then, but it is very helpful in other ways because you can see the frequencies present for different words. So one word may look different to another word in the frequency domain, which is really interesting and really cool. So this is kind of a funky way of using Fourier transforms within data science and within speech analysis. But this is kind of the main point that I wanted to talk about. This is something that I came across in the engineering tripos, which I thought was really interesting. And I was like, oh, I didn't actually know you could use Fourier transforms in this way. So I'm just going to very quickly and very briefly go through how Fourier transforms suddenly popped up within data science and within some random data that we got given, and how you can use Fourier transforms really effectively and really well to model data. So here is a graph of the average monthly CO2 concentrations from 1958 to 2019. So you can clearly see that there is a trend, and this trend is pretty much like that. It's going straight upwards. You can kind of see that it could be linear, there could be a quadratic trend, but also there are seasonal variations as well. If you take a tiny part of that data, here I'm looking at between 1992 and 1994, you can see that there are very big seasonal shifts in carbon dioxide emissions as well. So what we want to do is we want to make a model which accounts for both the seasonal variations as well as the overall increasing trend. So what we want to do is we want to find two functions, f of t, which is the entire long-term trend, and f of s, which is the seasonal variances within the data itself. So very quickly, I'm going to run through the long-term trend. This method uses a lot of linear algebra and a few cool and pretty funky matrices, which I haven't gone into much detail here, but if you are interested, I can release my code to show exactly how it works, and there's a lot more detail within the code, and it's very step by step, and it breaks down exactly how linear regressions work and how you can break it down to find the different coefficients. But essentially, what we want to do is we want to find a function that looks like this. So we have here f of x being the sum of two functions. The first part here, which is a linear, or it could be a quadratic function, depending on how much detail you really want to go into. And then the second part here, which is your seasonal variances, which is your sine and cosine part of the function itself. So as I mentioned earlier, you can just use linear algebra to find the regression coefficients for the line. These are just words that I'm talking, like saying regression coefficients. I'm not really going into too much detail about what they mean, just because it will take a while to explain how to go about finding them. But essentially what I mean by these coefficients is what I'm trying to find is all of these different beta values for the constants, for my x squared term, for my sines and my cosine terms. However, what we also want to find is we want to find these terms itself. We want to be able to find the frequency term and be able to find the frequency of the data and not just use sine of x, because that isn't really helpful because the frequency of that is way too large for the data that we're plotting. And that's where we can use Fourier transforms and break down the data really effectively. Very quickly, before I carry on, one measure that I'm going to be using, what's going to come up, is residuals. And what a residual is this tiny little expression here. And what it means is, so y is your actual function. That's the data that you've been given. And f of x is the function that you are defining. And what this is a measure of how much error there is between the function that you've defined and the data that you're working with. So Here is the data again of the carbon dioxide concentrations. So as you can see, if you have the mean concentration, you get this straight line here, this light blue line here. That's not very useful. It kind of just cuts across and it's just a line. Then we have the linear fit, which goes up that way. And then finally, we have the quadratic fit, which you can see fits the data a lot better than the linear fit. But the linear fit is a lot better than just the mean or the average of the data itself. However, as I mentioned earlier, this quadratic fit doesn't fit the seasonal variations. An easy way to find these quadratic or even cubic coefficients is just to use Python, the NumPy library, because it has a function called polyreg, and that will just give you all the coefficients that you need without having to mess around with all the linear algebra. However, if you want to look at the linear algebra, you can do as well, because it is fairly interesting. But carrying on, here we have the quadratic fit. But what we want to do now is look at the seasonal variations within the data. So this was something that I came across on Reddit, which I kind of find quite funny. And I was like, I've got to put a meme in my talk somehow. This is what happens if you don't have a decent trend in a model. Everything can just like end very badly. And according to this guy's predictions, we're all going to die fairly soon, which doesn't look quite right, but I thought was quite funny. So here you are, have a meme. But carrying on. So this is the original data, and then we've got the red line, which is the quadratic line of best fit. Now, these are the residuals for the quadratic model. And as I mentioned earlier, the residuals are just how well your function, the quadratic function in this case, fits the data which we've been given originally. And as you can see, it doesn't quite fit the data perfectly. However, all of it goes around 0. So all of it averages out to 0, which is really nice because it means that the quadratic function fits fairly well, but it's not quite perfect. However, if we look more closely at this data, and if we look at a range between 2009 and 2013, we can see that the residuals are actually periodic. The residuals actually change over time in a very periodic way, which is really nice because it means that we can fit a fairly nice sine wave to the residuals. You can't really see that in the overall data because it looks quite messy. But if you break it down and take a look at it from a smaller range, you can actually see that there is some kind of periodic variation within the data. And also there is a periodic variation within the residuals of the quadratic model. So what we want to find is, we want to find firstly the amplitude of this wave, and we want to find the frequency of this wave. And finding the amplitude and the frequency of a function is ridiculously easy if you take a Fourier transform of the function, because all it does is it breaks down the time domain into the frequency domain. So you can find the frequency and then you can find the amplitude of it. So we do this by using a discrete Fourier transform. A discrete Fourier transform is slightly different to an ordinary Fourier transform, but it's more so just the way that it's calculated. That's mainly because a computer can't actually solve anything analytically. It has to do it in discrete steps. So when you're doing something like integration or differentiation, you'd normally do it numerically, unless you're using a program like Wolfram Alpha, which kind of looks it up and doesn't fully calculate it. It kind of just like has a reference table. So this is the residuals transformed into the Fourier domain, into the frequency domain. We can see quite a lot of symmetry, which is really nice to see. But here we can see one dominant peak. This peak is the frequency in 1/s which is the most dominant frequency in the data. And due to the Fourier transform, we can now see that this is the one frequency that we need, which will mean that our model can now have a sinusoid added to it. And all we need to do is find the magnitude of this frequency, and then we can plot the sinusoid and add that to our original function, and then we'll get really nice fitting data. And this is what it looks like. This is what the residuals look like once we plot a sine wave to it. And as you can see, it plots it fairly accurately and fairly well due to the fact that we've taken a Fourier transform of the residuals and we found the dominant frequency, and we found the magnitude of this frequency, giving us a really nice fitting sine wave.
Sorry, can I just ask, why? So you had another large peak on the right with a frequency of something like 11. Why did we ignore that one?
11 here.
Like the big one.
I will come on to it. There's another couple slides which I'll zoom onto.
Sean says this is a lie thing, which is probably right. Yes, this is probably something I just forgot from methods.
Yeah, it is.
Okay.
Exactly that. It's aliasing. But
yeah.
If you wait a tiny bit longer, there's another slide which I'll come on to using a different set of data, where this becomes fairly important as well.
Okay, thank you. Yeah.
Yeah, that is a very good question, and I will come on to it very shortly. Okay, carrying on. So this is a plot of the final residuals after you've added the sinusoid to your quadratic function. This is the scatter plot of your residuals. And as you can see, there's a really nice Gaussian distribution of the residuals about 0, which means that we've come across a really well-fitting graph because the residuals aren't too spread out and they're spread out fairly evenly. But what happens if we have some data which isn't as nice? So here we can see that the data has a vague linear correlation, but it doesn't seem to have a nice periodic variation. So this here is the linear regression for the data. But if we take a look at the residuals of the data, there isn't any periodic variance. It's kind of just, it looks very odd and doesn't look very systematic. And this is the frequency domain plot of the residuals. And this is exactly the point that you were making earlier about me ignoring one of the frequencies and about aliasing and the way that the data works. If we have some data which isn't that nice, which isn't that very well fitting to a model, we can get Fourier domain plots which look quite rough and quite ugly, which look something like this. The data itself, which I'm analyzing, is actually fairly random data. I'm analyzing the amount of users of the tube throughout a time period. I think it should have gone down by now. It should be reduced a fair bit because of the lockdown, which should be quite interesting to analyze. But this is the Fourier domain plot of that data. And it doesn't really look that nice. It looks a bit messy. But we can still use this. What we can do is we can find the peak value here. In this case, I've taken any amplitude which is greater than half of the peak amplitude. So that's greater than about 1,700. So about here. So anything above that region, I have taken to be a dominant frequency. And what I've done is I've used the magnitudes of these dominant frequencies to plot the data. If I move this bar lower, it means I will get a more accurate data set and a more accurate graph. But it also means that I have a lot more computation to do. And it's just a lot more work in terms of finding all of the different frequencies present. And it's not necessarily useful if you're just creating a model. So in the exact same way that I found the frequencies and the amplitudes from the Fourier domain plot of the first set of data, I've done the exact same thing with the residuals of the second set of data. And this is the output of that. And as you can see, it kind of fits the data, but not very well. it kind of jumps around a little bit, but it's a lot more better fitting than the linear regression line which we had to begin with. And this here is the final plot of the second data set. This here is the linear regression line added to the sinusoidal variance and function that we created using Fourier transforms. As you can see, it fits the data fairly well. We've still got lots of bits down here which doesn't really fit the data, and this is due to the fact that I only used half of the maximum amplitude as my cutoff point. If I made that lower and lower, it would mean that my data would fit a lot better, but it also meant more computing. And for seemingly random data, it's not really that useful to go to more depth and more detail. But I just find it really cool and really interesting how you can have data which we've genuinely collected from people using the tube, and then we can decompose that and turn that into a really nicely fitting model using the Fourier transform and using the frequency domain plot of the residuals of the data. And that's essentially what I really wanted to share with you, how Fourier transforms can pop up pretty much in the randomest of situations and in really useful situations when it comes to signal processing and data analysis, to give really powerful insight into the data that you're analyzing. And that's pretty much my talk. Hopefully this will give you new insight into where Fourier transforms are used and how they can be used as a really powerful tool, and how in general maths can be used in a really effective way for different applications and for different uses. Yeah, this is how Fourier transforms are used. If anyone has any questions, I will switch into the chat now.
I think if there aren't any more questions, let's just thank Sheamol for the really interesting talk. Yeah, thanks a lot. It was quite cool to see the applications. If anyone wants to know a little bit more about how Fourier analysis is used in pure maths, there'll be a talk in 2 weeks' time about how Fourier series have been used by Maria Wierzowska to prove her quite well-known result about sphere packings, like the densest sphere packings in any dimensions. So that'll be in 2 weeks. Okay, yeah, and now let's just thank Sheamol and thank you everyone for coming, and it'll be about a 15-minute break before the next talk.